Okay, so we talked about algebraic optimization, and then we talked about declarative languages on top of the algebra in order to simplify expression and in order to avoid specifying to the computer exactly how to do it, right? We want to leave that open and let the database figure that out. But we stopped at what I'll call logical optimization. And I want to talk a little bit about the physical level optimization. And what I mean by this is that even after you specify, we hinted at this last time, but even after you specified the order of operations, we haven't yet specified every detail needed in order to actually evaluate the query. Okay, and let me give you an example of that. So here's a simplified version of a query we looked at last time, where we say for every order, we want to find all the corresponding items that were part of that order, and that's it. Last time we had an extra condition. Oops, I'm actually pointing with the mouse, but you can't see that because I'm on the wrong screen. So for every order, find the corresponding items that match. And last time we had another predicate down here, and this time I've taken that out. And so the algebraic plan that this translates into is very simple. It's just a join of the two tables, and that's it. So you think we're done, right? We're going to join order and item, and we're finished. Well, we got to specify how we're going to do that join. And so let me tell you about a couple of the options here. So one, in sort of very high-level pseudocode, looks like this. We could say for each record I in item, and for each record O in order, check to see if those two records agree on the order fields, on the order attributes, and if so, return it, and that's a join result. Okay, you know, they match. So fine. Another option is for each record I in item, insert that record into some sort of data structure, and here I'm going to call it a hash table. Now, I'm not too concerned about what exactly that is. And then second, for each record O in order, go look up the corresponding records in that data structure that we found, or that we built, and return all the matching pairs. Okay, and if it actually is a hash table that we're talking about, then this lookup could be pretty efficient, right? It could be constant time, amortized constant time, right? And so now this one says, well, for every record in item, go scan every single record in order. And so we have kind of an n-squared complexity going on here. And here we say, well, for every record in item, put it into a data structure, and then after that, for every record in order, go look up those records in the hash table. And if indeed this is constant time amortized, then this is a sort of linear time algorithm. So there's two different ways. So I argue that there's two different ways to implement this join, that both of these are valid. Okay, so which one is faster? Well, I've sort of hinted that perhaps option 2 is faster, but in practice it may or may not be. And so, you know, I would pause here and ask the class to answer the question, but since it's over video I can't do that. I'll give you a moment to think about that. But I want you to think about why this one in particular might be faster in some cases than this one, even though it seems like it should never be. Okay. And let's see an example maybe in a second. So leaving that question hanging open, I want to make the point that you have access to this underlying algebra. This isn't something that's that's purely sort of theoretical, right? This is something that you can use tomorrow if you work with databases at your job. For example, in this particular product, Microsoft SQL Server, and in fact in all the products you're going to use the same sort of mechanism, but you can explain a query, and that will give you access to some form of this algebra that I've been talking about. Okay, so if you take a query, and here I've changed the query, I've changed the schema yet again. This table, this Reuters table, is one you'll be working with in the homework. I've written a query here, and I've explained it. And what shows what the SQL Management Studio gives back to me is a little algebraic tree, kind of like the ones I've been drawing here, just in PowerPoint. Okay, and so this one says a hash match is going to be used to implement this join condition. This one's kind of a complicated join condition for a reason I'm not going to explain right now. But it has two leaves, and then they get joined with this thing called a hash match inner join. Okay, and so this is very much like the hash table example I gave on the previous slide. But I want you to take a look at something. So here I've taken the exact same query, but I've added an extra condition where I'm only looking for words equal to parliament. I probably should explain this schema a little bit. So the Reuters data set gives you term frequencies. You have 3 columns: doc ID, or let's just say doc, term, and frequency. And the frequency is how often that term appears in that document. Okay? And so this is the table you'll be looking at. All right. And so here what I've said is I'm looking for pairs of terms that co-occur in a single document is the previous query I was looking at. And now I've said, well, look, I don't want all pairs of all pairs of terms. I only want terms that co-occur with the term parliament. Right? So perhaps lawyer co-occurs with parliament frequently. So I'm looking for all the terms that co-occur in some document with parliament is what this query is expressing. Okay. So now, what I want you to notice, though, is that when I explain this query, I get a different physical plan. The logical plan looks the same. It's still got scan, scan, and a join, but the algorithm to compute the join has changed, and now it's this thing called nested loops. And that nested loops corresponds exactly to this pseudocode here. That's why they call it nested loops, the outer loop and the inner loop. So exactly the same thing. And so it chose to do this nested loops plan even though we argued that it was an n-squared algorithm and it probably wouldn't be chosen very often. So why was it in this case? So if you think about it, one of the sides of this join is only dealing with those terms, or with the occurrences of the term parliament in a document, which is a very small relation. And so it's a very small relation, and this nested loops algorithm could be very, very efficient and faster than dealing with the overhead of actually constructing this hash table or constructing some data structure. Okay. So the main takeaway here, as opposed to the details, is that different physical algorithms are appropriate at different times, and that this declarative language, and thanks to the declarative languages and thanks to algebraic optimization, the programmer doesn't have to worry about any of that. They don't have to make that choice. Okay, so this is a very, very powerful idea. You just express the query, and the database does the rest. All right. So fine. And just to point out, this is not just something unique to SQL Server. You can generate these kind of algebraic plans in Postgres by using explain. And in fact, they look kind of nicer. And here's these hash joins again. This actually shows you, whoops, excuse me. This shows you where it's building the hash table as the step 1 and then probing it with the step 2, and same thing here. And this is another operator that we didn't talk about where say you're going to count all the records that match some count all the members of some group, I'll put it that way. And so the hash here is on group ID, and you can apply aggregate functions to the rest of it. But I shouldn't give such a high-level view of that without talking about it more. So let me skip that altogether. Okay. So fine. So the algebra really does exist. You can look at it directly just by using the keyword explain, and I advise you to do so. If you work with databases, you should be using explain all the time to try to understand what's going on. All right. Another point I'll make is just that this matters. This is not directly from SQL, and in fact, it's not from a commercial database. It's from some research that we do in my group. But the point is the same here. These are actually different physical plans for the exact same query. And in fact, here I'm doing something in parallel. So this is actually number of processors being applied. And so as you go from 4 to 16 processors, things go down a little bit, not as much as we'd like. Actually, they should be sort of going down quite a bit. But the point is that each one of these plans is doing a very different amount of time. Well, these two are kind of the same, but the difference is pretty important. And so ignoring these opportunities and sticking with only the plan that the programmer specifies would be a big mistake. Okay. And then another illustration of this that's a little bit hard to stare at, but let me give it a whirl to try to explain what's going on here. This is by some very nice work by Haritza and et al. At VLDB 2010, but there's a whole series of papers on this work. But they try to visualize the space of possible query plans. And so what the two axes are here, this is all for a single query, but the parameters to that query are changing. And so this, in fact, says something about the supplier account balance, and this is a parameter on the sort of extended price, and they change the values of these parameters in the query. So imagine the same syntax, the same select star from something something, where some condition equals extended price and some other condition equals account balance. And just by varying those two knobs, you get this really rich tapestry of different plans being selected by the optimizer. So each color in this space represents a different query plan, a different algebraic query plan selected by the optimizer. Okay, and so I think that the takeaway here is just that it's a very complex decision being made by the databases, and necessarily so. They actually, these different plans actually matter. They don't show that here, but you can actually show that this choice of plan databases tend to do a pretty good job of finding the right plan, and that I argued in the last slide that this can actually matter, that the difference in the time can be pretty significant. Okay, so leaving this kind of complexity up to the programmer is can be a big source of loss, right? Hiding this complexity is a huge win.